Welcome back to Machine Learning 1. And today we begin our not so fun journey about learning math and probability. Well, at least I think it's fun, but I don't know if everyone's going to think it's fun. But the next 4 lectures or so are going to be about math and probability review stuff. Some of the stuff hopefully you've seen, some stuff maybe not. But it's all sort of like the basics that you'll probably need for other classes anyways. So this will be useful. And I don't know, like, fortunately or unfortunately, the notation is like important in most classes. And if like you don't understand what the symbols mean, you probably don't understand what's going on. So you're gonna have to kind of learn this stuff one way or another. Okay, so getting into things right off the bat. So today's going to be math review. There's going to be nothing to do with like probability stuff, and we're going to cover all sorts of things like what sets and tuples and vectors and functions and integrals and derivatives and so on are. And we probably will finish this stuff like midway next lecture, and then we'll do like 2.5 lectures of probability and statistics stuff. Okay. But before just like jumping straight into all this math notation and so on, because that might be even more boring than what I'm going to do now. I want to like maybe motivate this like setup that we had in the previous class with what it might look like with some of the symbols, and then hopefully we'll be motivated to like understand what the symbols are, and then we're going to kind of return to it and be like, okay, yeah, we learned these symbols, and now we kind of know what they are. So let's try to do that for the next like 15 minutes or so, and then we'll jump into me, kind of talking and writing stuff on the iPad. Okay, another thing to note about just logistics. So I shared these notes on the website in the schedule tab. And as you will see, like each day, like for each lecture, there's like, the lecture video or like the topic, and then there's going to be these notes that I post before, and then there's going to be the video I post after. And the way I'm going to do it for the notes is that I'm going to have like a kind of live version of the notes, which some stuff is filled in and some stuff is not. And then I will fill it in during the lecture. And then once we finish that section, I will post the corresponding final version of the notes with stuff filled in. And for the math and probability stuff, unfortunately, to get through things more quickly, most of it's kind of like filled in, and we're just going to like talk about things, kind of like slides. And then when we get to supervised learning and like the actual machine learning stuff, I'm going to do a lot more writing, kind of like whiteboard lectures. Okay, that's the background. Now let's get started. Okay, so we said we're going to talk about like the supervised learning problem for basically the whole course. And that was like this idea of learning from this like randomly selected batch of labeled data. And let's try to define this a little bit more formally. So we saw that the rough idea was like we had this experience, we do this learning from the experience, and we produce some knowledge. And in the example we saw for like this house price prediction business, we had this thing, which we're going to call a data set in a second. And then we needed to produce this knowledge, which was like a function called a predictor. And then there was some like function in the middle that did this thing. And so a little bit more formally, it's going to look something like this. And yeah, so this thing on the left is we're just going to call it a data set. And that's like standard in machine learning. It's going to be like an object that's going to look something like a tuple of tuples. It's just going to be like a sequence of feature label pairs. You're going to have like some amount of them. Like these are going to be your feature label pairs. They're going to be tuples, and then you're going to have to like have some amount of them. Here there's 4. These objects are going to be defined like when we get into it. Don't worry. There's a question already.
Yeah. The notes for
Oh, that's awesome. I'm going to spend about 10 seconds checking if these notes work. Oh, I think I know what the problem is. Okay, we're going to spend about 30 seconds for me to commit the new version of the notes such that people can download this. So, sorry. I decided to append the title of the notes with the word live, and that's why the link doesn't exist. right, the notes work locally. I'm just going to push the changes and we will get back to business. Okay, the notes should be up in like a minute and a half when GitHub builds their website, I think. And if they're not, please tell me. All right, back to the story. So we were trying to define this like experience, knowledge, learner business. So these are going to be the objects that we're going to define more formally soon. And yeah, so there's going to be this thing called a data set. We're going to try to like do this in a second. The knowledge that we produce is going to be called a predictor. That's the word I'm going to use throughout the course because it's going to do the predicting. It's going to like take in a new feature, which would be like the number of rooms in a house is going to predict the label. But oftentimes, I'll also mix up the words that are commonly used in machine learning, such as this predictor is also called a model. Or sometimes in like more classical machine learning theory world, they call these hypotheses. So this is like the hypothesis of what generated the underlying kind of data in some way. Yeah, and I'll probably use the word predictor and model the most commonly, and this is usually maybe what's most often used. And this will just be a function that should make complete sense. But we're going to define functions. You probably know what functions are, but we'll talk about them. And then this one's going to be more complicated. It's going to be like the learner, right? What I said, this learner takes in this like giant thing called a data set. Right now we have like a table of things. We're not going to use we're going to use some, the mathematical object we'll use is this. And that's what the learner is going to take in. It's just going to be a function that takes in this data set thing. And it's going to output a function. And so we're going to need to like maybe define this a little more formally to see what that looks like. And that's going to be kind of our goal for today. And let's try to just do it like roughly right now. And some notation doesn't make sense, well, it'll be defined. So let's try to make this like data set. So we're going to start with a data set. That's what this like square here is. Okay. We want to make this like, some general mathematical structure. Like in general, you're not going to have only 4 data points. In general, your data points aren't always going to just have one feature, like one piece of information. It might also have like number of rooms and correspond maybe like distance to downtown and so on and so on. So we're going to need to like, make this a little bit more general. So let's start with like, we're doing that. So first thing is instead of like the feature being the number of rooms, in general, this is going to have a different title. It's going to be, as I've been saying enough times now, it's going to be called the features. All right, so these objects are called the features. The other column of the table is not always going to be the price, of course. It's going to be called like the label. And the label is usually used for these like classification problems, or the other thing is called like the targets. So it's going to be like the label or the target. Okay, great. We've given these better names. And we're not going to have like numbers in math. We usually like to use variables because they can take on some arbitrary values. So let's start by writing all this. Okay, so first of all, the features, we're going to use the variables x for it. And like the first one, the value 2 that we just saw, whatever it was, we're going to call that like x1, and then you would have like x2. And in general, you can have more than 4 features. So we're going to give it a variable as well. And so we're going to have up to xn. And so like n is going to be the number of features you have. This is just going to be a variable we always use to denote the number of features in the rest of the course. So remember that. Okay. So that's going to be the number of features. We're going to talk about them in a second, a little bit more. And so correspondingly for the labels, we'll also give them like a variable name. And that variable name is going to be y. So I don't know, kind of makes sense. You're mapping like x's to y's. So these will be like y1, y2, up to yn. So we have n feature label pairs. And like that's like really what our data set is going to be. Okay, so just like in words, I'm going to give this data set a variable as well. It's going to be like this calligraphic D. And just in words, the data set is going to contain like this variable n feature label pairs. Okay, so we're starting with things like in words kind of and giving things variable names. And we'll define, okay, So this is your D. What is like, I gave the D a variable, let me just define it a little bit more precisely. It's gonna be like as you would kind of expect, you're gonna want it to be like, these feature label pairs. So it's gonna be like x1, comma, y1, right? And to denote that they're like a pair and they have some order, we're gonna use these curly, and not these regular brackets. And these are denoting that this is a tuple. So this is gonna be like the first feature label pair. Then you're gonna have another one up to basically the nth feature label pair. Right, this makes sense. I've just taken the objects in the table, wrote them out as this sequence, and usually we wrap this whole thing in like brackets as well to denote that the whole thing is a tuple of n feature label pairs. And roughly speaking, we do this because we want to allow, what we'll see is tuples will allow duplicates. And if our data has multiple houses with the same number of rooms, that'll be important to know, okay? But this should make like complete sense, right? You're like, you just took your table, mapped it to this like mathematical object, and that's your data set. Okay, let's come back to another like point I was mentioning, which is like the number of features you might have may vary as well. Like we saw that you might have maybe one feature like the number of rooms, but you could have more. You could have two, you could have three, you can have, well, we're going to use a variable to describe the number of features, and that variable is going to be D. Okay, so in general, these x1s till xn are going to be vectors, and I'll use this like, I guess, arrow above them to denote their vectors. And they're just going to look like vectors that have like, they're going to be x11, which is like the first index of that vector, up to, in general, the dth index of it. So you can, this just denotes that you could have D features. And I had a transpose to denote that this is a column vector. Okay, so that should make sense, and that's the same story going to be for x2 as well. So it's going to be x2 dot dot dot, and this dot 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 notation will be used throughout the course. It's actually very common in math and quite formal, if you could believe it. And it just means, like fill in the stuff in the middle, because I'm not going to write out D objects for you. Okay, and so yeah, this continues in the same way. And so xn will be like xn1 up to xnd. Okay, and that should make sense. And so, yeah, these features, this is going to be like the first feature, this will be like the second feature, this is like the first label, the second label, and they're just D-dimensional vectors. D, in the case of the house prices we saw above, was equal to 1. There was only a single feature, the number of rooms. Okay, and so just to continue with formalizing things a little bit more, in general, these like xi vectors, I being some number between 1 and n, are going to belong to some set, calligraphic x, which will often just be, and by often I mean like always, is just going to be RD. It's just going to be the D-dimensional vectors. But I will write this calligraphic x quite often. This is going to be the set from which our features come from. But first, this is different depending on your problem. And I'll just finish writing a few more things and then I'll take some questions. And the labels, these yi's, are going to belong to a set as well, like calligraphic y I'm going to use for it. And here it will change depending on if you're working with like regression or these classification problems. And so like in the regression problem with house prices, this y might be something like the real numbers. It's really going to be like the positive reals, and it's going to represent the prices of houses between 0 to like, I don't know, as large as it gets. And just to be a little more formal, this I is going to be any number between 1 and n. Okay. And so let me just write this a little bit more intuitively in English. So this set X is going to be the set of our D dimensional features. Okay, so our features are D-dimensional. They all come from the same set. In this case, it was like D-dimensional vectors. And Y is the set of labels or targets. Right. Okay, I'll take any question about this before I move on to the next two objects. Yeah. Oh, so we'll get into it. This is just the transpose of the call or the row. So this is the way I've written this. This is going to be a row vector. The transpose just makes it a column vector. And in general, you'll see with vectors, we're going to usually, like when we write a vector, it means a column version of the vector. That's it. We'll talk about it when we get into the math review. But if you know linear algebra, this should make complete sense. Okay, great. So yeah, you can see there's some math stuff, there's like, this calligraphic X, R to the D, R's, this coming from a set. I don't know, maybe it's not that complicated, but it's important that we know what these objects are, because now we're going to talk about some, like what these functions look like and what they're doing and so on. So let's start with like the kind of the thing we're trying to do. We're going to try to produce this model or predictor that is going to, and the important thing that I haven't kind of mentioned is I haven't told you what's the real objective, like we haven't formulated this. That's going to come like maybe 5 lectures from now, but roughly speaking, it's going to be that we want to predict new labels well. Like you're given a new feature, you want to predict the label correctly. Okay, but what does that object look like that does the predicting, the model? Well, it's going to be a function, and so that function, I'm going to call it f, okay? And that's going to be like, this is a function. And in English, so like, okay, in general in this course, I'm going to try to use blue to give like the, English intuitive explanations of things, and black will be the mathematical definitions, and then other colors are just going to be random. And red usually means bad. Okay. And so yeah, this is a function from, as you might expect, from features to labels. Or targets. I'm probably going to use the word labels throughout, but sometimes people call them targets. And like mathematically, we'll see a symbol like this. Our function f will be a function that maps from objects in X, X contains features, to elements of or objects in the set Y, which are labels. This will be the notation we use. That should make complete sense too. And so like a super simple example that we kind of have seen from like the previous class is like, one example of this predictor is a line, right? Let's imagine house prices. Maybe like, if you have one room, maybe you predict like $200,000 house. If it has 2 rooms, maybe it's like 400,000. If it has 3, maybe it's, I don't know, 600,000. So the way I describe that would be like 200, denoting the price in thousands, multiplied by the number of rooms, like X. And this one should be like the first, okay, I'll just put X. X is here, just one dimensional. It's the number of rooms. Okay, that should make sense. And then you can also like, I don't know, like offset the line by maybe 100, because you think when there's one room, it starts at 300,000 and then it moves up. This is an example of, your predictor. And to be like clear, your X here, your set X is just the real numbers. It's one dimensional. And Y, well, it's also going to be equal to reals, even though it's really the positive reals, but yeah. Okay, that should make sense. And now let's get into maybe the most complicated. Oh yes, and so someone that asked online was like, can you repeat questions that students in class ask so we can hear them? Absolutely, I will try my best, but I can guarantee you that about 50% of the time I will forget. But we'll still try. So just to repeat the previous question, there was a question that I'll probably get in a few more minutes, which is like, what does the notation T mean here? So this means transpose for vectors. I'll probably get a couple more questions about notation before we define things formally. Okay, let's get into this last object, which is this learner thing. And so it's easy to write what this learner is going to be in words, right? First of all, as with the predictor function, that's, okay, maybe I'll, yeah, and as with the predictor function, f, we're going to give this like learner a kind of a symbol, like so that we can talk about it abstractly. And that symbol is going to be this like calligraphic A, kind of used somewhat often for algorithm, and it's going to be a function. From that, it's going to be a function from data sets. And I just want to make this like, the reason I'm making this very clear is because the understanding that this learner is mapping from data sets will be very important, because you never really know what data set you're going to get. And if the data set changes, how are things going to change? These are going to be very important questions. It's very important that we actually see that this learner is going to take as input a data set. So it's a function from data sets to predictors. Right? That's what it's going to do. And so so we're going to need to define this thing formally, and we will, in the same way that we have above. But maybe before doing that notation, we'll come back to it a little, or maybe I'll do it in a second. Let's just look at an example of what might a learner look like. And this learner is going to be kind of naive, and it's going to be the learner that kind of just memorizes the data, right? Roughly speaking, what's going to happen? It's going to you're given a new feature, right? Any value of X, let's say any number of rooms. What are you going to do as this naive learner? You're going to just look at your data set, right? You've been given a data set, and you're going to see, does my data set have that amount of features? If it does, I'm just going to predict whatever the label is for that number of rooms, for that feature. If there's multiple, maybe just pick the feature with the lowest index or something. And if I don't have it in my data set, well, who knows what I'm going to do? I'll just output the same number of 0 or something like that, because I don't know what to do. I've only memorized the data. And that's not going to be a good learner, but it is nonetheless maybe the first learner you will think of is just to memorize the data set. And then at least you get the things right that were in the data set. Okay, so let's try to define that object. So the learner, takes in a data set. We've defined the data set. It's this calligraphic D. Okay. And it's going to output a function. So let me just give the function a symbol. I'm going to commonly call that function the predictor f hat, kind of for the estimated predictor. Okay, now all that's really left, okay, let me maybe say one thing, of course, this f hat is going to be a function from features to labels, just like above, right? This is, as it should, it's the predictor. Okay, so at this point, all that's left is to tell you, how am I deriving this f hat from the data, how does it use the data such that it's going to output labels from features? Okay, well, here's going to be my definition. Just as, how do you define a function? You say, what does it do for every input? What is the corresponding output? Okay, so let's define its input-output behavior, f of x, f hat of x. Okay, it's going to be this piecewise function, and this is going to be there's going to be two conditions. So first condition is if x equals to xi for some I, that's from 1 to n. Hopefully that's visible. Just if this feature that you've been given, x, matches a feature in your data set, then first of all pick, and if it does, then just pick I to be the lowest index. So just I is going to be the lowest index that matches the corresponding feature. And what you're going to output, okay, so this is the condition, and what you're going to output is just the corresponding yi, the label. So once again, if you have a feature x, you're going to go look through your table or through your data set, and you're going to be oh, does x1 match x? If it does, output y1. If not, move on to the next one. And do this until you encounter the first index I that does this. Otherwise, this is going to be the otherwise condition. What happens? Well, what happens is you have no idea what to do, so you just output anything you want. Here I put 0. Maybe that's a terrible prediction. Maybe you want to output 500,000. Maybe that's just your average guess of what the house will be or something. Again, this is an example of a learner. We're going to think of more sophisticated learners. Let's think of one right now. Above here, I said we have a learner a predictor that is a line. How do we get a learner that predicts a line? Well, you can see that roughly speaking, what's going to happen is you're going to somehow need to look at the data set. And how do you decide on the line? Well, you need to decide on the slope and the y-intercept. And so there's going to be a procedure. It's going to be called linear regression, in which you use the data set to decide on the slope and the y-intercept of your line, which will then be your predictor. And you can imagine with higher dimensions, these are no longer lines. They're going to be these hyperplanes that then predict things for multiple dimensions. And what you're going to need to do is decide on the corresponding kind of slopes and the y-intercepts. Great. And then we'll have more complicated functions later. How are we going for time? Not too bad. Okay. So what's left really is just to define kind of what is this learner function going to be, how is it going to be written? And this is probably going to be the most complicated thing today. And once I do this, we will then get into the math. Okay, so I need to map, remember how these functions work at a high level of what I said, is mathematically is going to be like a function is going to be a map from a set to another set. So I need to define the set here for the learner, that is the set that contains all data sets. Right, this was a particular data set. I now need the set that's going to contain all possible data sets of length n. And it's going to map to predictors, which are functions from x to y. And so the way this is going to look is I'll do the mapping part first. So somehow here, we're going to need to write down the set of data sets. I'll make it formal in a second. And that's going to map to the set of functions, which are predictors. And particular is going to, the way we're going to write this is going to be, this is actually formal, it's going to be like the set of functions such that, that's what this bar is going to mean, such that those functions are maps from x to y, or maps from features to labels. Should make sense. And then this set of data sets, we need to fill this in as a mathematical object. And if this stuff doesn't make sense, don't worry. It will, hopefully, by the end of next class. And the data set object, okay, somehow I need this like, n-length tuple that takes in feature label pairs. And hopefully something like this will make some intuitive sense, and we'll see how it makes formal sense in a moment. So this data set is going to belong to the following set. So first of all, a feature label pair. So a feature belongs to the set X. A label belongs to the set Y. If you want to combine them to be an ordered pair, there's a procedure called a Cartesian product written with a little x. Just basically maps them into all possible pairs. And then if you want to do that, so that will give you one of these. And if you want to do it n times, you would write this n times. However, people have come up with like a shorthand, and it's actually how we define these like d-dimensional real numbers and vectors. And that shorthand is, let's not do this, and let's put the number of times we do this Cartesian product in the superscript, n. And so like an example we've already seen is this RD. So this is like take the real numbers, combine, do this Cartesian product d times, and now you have a tuple, which is a vector, of d-ordered objects. Yeah. We'll see this more formally in a moment. And so yeah, that's what's going to be here. So it's going to be these n feature label pairs. Those are just the set of data sets. This data set up here belongs to this set. There could be, if you change if you change one of the labels, oh, that's another data set. That is inside this set, and so on and so on. Okay, and that's it. So this is going to be a very important object. And, in some machine learning courses, this is not emphasized, and it's not written in this like super formal way. And to be honest, you can probably get away without knowing this like exact notation. But I'm going to urge you to like kind of be aware of it, and to remember, because you're going to see it's going to be very useful to remember that this learner really is a function of the data. And if the data changes, you're going to have all sorts of effects that we're going to talk a lot about later. Okay. So shall we get into the math now? Hopefully that was enough motivation. Is there any questions? And if they're not like about the notation, I'll take them. Yeah, up there.
So the set of data sets
Is essentially what, sorry?
Is essentially the feature label.
So the question is this set of data sets, is this set essentially D? The answer is no. What it is the set that contains one of these, right? So D belongs, it's one of the elements of this set. However, this contains lots of data sets. So like, this is not formal, but you can roughly think of this object here as like a set that contains like data set 1 and data set 2 and so on. And there's going to be infinitely many of them ever. And so this D was just like a particular one that I had chosen. If I were to change like one of the labels or two of the labels, that's going to be a different data set. All of them are in this set. And yeah, they're just like, If you wanted to write the set that contains all possible data sets, this is what it is. And we'll build up to it very soon. Okay, let's start. So we start super simple, although maybe it's not that simple. So we're going to start with sets. Maybe also, so we're going to start with some topics like the first 20 minutes that are maybe not super emphasized. They're actually very much like topics that are studied in pure math style courses. However, like you use all the notation later, as you'll see, and it's just kind of a disappointment if you don't know where it comes from, because then you're always like, what the heck is going on? So let's spend this time defining some of these things. So let's start with sets. Okay, before I start with sets, let me tell you one like fun side note. So like all of like this math stuff that you work with and so on, is like, okay, the short story is like everything you do in math is based on some like what is called like a formal system. And that formal system has like some underlying set of axioms that you assume are true, and then everything else in math is built up and so on. And so like everything you've worked with in calculus and discrete maths and so on are all based on some like axiomatic system. And that axiomatic system is actually based on set theory. And it's called like this Zermelo-Fraenkel set theory. And so anyways, just for the people interested, like set theory is very important to like build up the axioms of math. But for anyone else that doesn't care, let's just define these sets. So in words, as I said in blue, the high level idea is going to be that these sets are going to be just like some collection. The word collection should have zero meaning to you other than the English meaning at this point and throughout. And just like it's a collection of some distinct and unordered objects. Okay, these objects are distinct, meaning they're different, and there's no order. So just like imagine you had like some bag and you just put in some objects in it. So you can put in anything in these sets. Sets are denoted with these curly brackets. Okay, and you can put anything in them. But if you put something in that's a duplicate, then that duplicate, like it goes away, it doesn't mean anything, and so these sets will be the same. So like this set will be the same. Technically, this set isn't even like it's not even like a formal definition of a set. You should never really write this, but people write this and say like, oh, these are the same thing. You can't put duplicates. And you can put anything in these sets. You can put like cats and dogs, and you can, I mean, like if this was your labels, you can see you can put a cat and a dog in that set. And like that's an example of when your labels might be cats or dogs. That's calligraphic Y set. Turns out that these things you work with, like numbers, like natural numbers, which are like all the integers from 0 and larger, and the real numbers, which are like all the numbers you probably can ever think of, other than the imaginary numbers, are also all defined as sets. And if you ever take what is called a real analysis course in like the math department, you'll spend like a good 3-4 weeks defining these objects using sets. And it's a whole ordeal, and it's kind of fascinating. But we're not going to define them, and I will just tell you what they are, roughly speaking, by what the objects in them are. Okay, so these are all the sets, and there's something called an empty set, which we'll probably never use, but it's denoted as this symbol, and it contains nothing. As you saw already, we're going to use variables to denote sets, and usually they're going to be calligraphic letters, or calligraphic symbols, calligraphic letters, such as like calligraphic X, Y, and Z. And that calligraphic D is going to be the kind of like outlier, which we like, yeah, I'll talk about it later. So yeah, we'll usually use calligraphic letters to denote these sets. And so yeah, again, an example is like you can use calligraphic X to denote the set that contains the numbers 0, 1, and 2. Or there's omega to denote the set that contains cat and dog. I will use these values of these symbols, I think, a few times, so maybe sort of remember them. I'll remind you as well. Okay, so we can also talk about how many objects are in sets. The notation for this, or at least the word for this, is called the cardinality of the set. It's just the size of the set, really. But it gets a little bit tricky because things can get very big and infinite. So when you start with these finite sets, meaning that there's only a finite amount of elements in the set, such as this set here, you count the number of objects like 0, 1, 2, there's 3 objects. So the cardinality denoted by the what looks like absolute value symbols is 3 of this set. For the cats and dogs set, since there's 2 objects, it's 2. Once again, we'll use this somewhat often. And the amount of objects in the empty set is 0. Okay, so here's where it gets interesting. I guess I didn't write this, but so the cardinality of the natural numbers, as you can imagine, is infinite. Right? You give me any number, I can always add 1 to it, and that's another number, and it's in the set. Okay? The cardinality of the real numbers is also infinite. It turns out that the cardinality of the real numbers is a larger infinity than the cardinality of the natural numbers. Okay? So we give them a name. So it turns out this is also going to be very important in a second. Oh, I guess I talk about it in a second. But anyways, this is called countably infinite because you can kind of count them. You can enumerate them. There's 1, there's 2, there's 3, and any other like object that you can have this like mapping to the natural numbers is called countably infinite. And this is called, unsurprisingly, uncountably infinite. And yeah, as I said, these are not the same size. And the fun fact for this is that anyone also familiar with math stuff, there's a famous hypothesis called the continuum hypothesis. It was like in the, actually, I don't remember how long ago this hypothesis was. I don't remember who it's by. But it was at least proposed before like the 1960s. And what's the hypothesis? Well, it is that there exists some set that has a larger cardinality than the natural numbers, but less than the cardinality of the reals. Okay, so the claim is that there's some set that has some size that's between both of them. And so, you know, completely useless question for the most part, but people ask these questions for fun in math. And guess what the answer to this question is? The answer is, we'll never know. And very formally, the answer is that someone called like Paul Cohen or something actually proved that you can never prove if it's true or false. And so after that, there was a whole like series of people proving things in math. So like in discrete math and so on, you probably heard of proofs, which is like you prove a statement is either true or false. Well, guess what? Next time someone asks you to prove something, there's an alternative, which is that you can prove it's unprovable in our axiomatic our axiomatic system of math, which is what they did for this question, and then they ended up doing it for a bunch of other questions. And there's even questions in machine learning that we won't get into that some people showed as well, that like, you want to answer the question of whether you can learn a good predictor with this much data? Guess what? You can never prove it. So anyways, just fun fact, completely useless for the course. Okay. But the notion of knowing that there is this countably and uncountably infinite will be very important because we're going to get into probability theory, and there you're going to hear about these like continuous and discrete random variables, and they will be defined through the sizes of their sets. Okay. Countably infinite. So yeah, the rough idea is like, yeah, as I said, if you can like list all the elements in the set, then it's countably infinite. So like the natural numbers, I can like enumerate, list them one after another. Another set that's not the natural numbers is like just take all the elements of the natural numbers and then pick the x's that are even. And this notation probably doesn't make much sense, but we'll define it in a second. But yeah, if you take the set that just, you know, removes all the odd numbers, still countably infinite. And uncountably infinite sets are like the real numbers and intervals and so on. So like, let's say all the numbers between 0 and 900. Okay. We'll get into this interval notation in a second as well. Okay, so it turns out to be also useful to talk about formally about elements of sets with some symbol, and like whether a set is smaller than another, whether it's inside another set, and so on. And this notation will be important, and there's not too much of it. So first, let's just look at a picture. This is the picture. So we've seen that the real numbers has a bigger cardinality than the natural numbers. It turns out not only is it a bigger cardinality, but it also contains all the things in the natural numbers and more. So that's like denoted usually by like a picture like this. So like the reals is like this big circle. Okay, it has like all the numbers except for the imaginary ones. Then there's the natural numbers, which are a subset of the real numbers. Then there's like the set calligraphic X that we saw before, which was the set 0, 1, and 2. Of course, that is a subset of the natural numbers. And it's quite small. And then there's a set that's just incomparable to the others in some sense, which was this omega, which contained cat and dog. It's not very big, but it's not in any of these. Okay, and so let's talk about how we write this with this set notation. So we're going to have first inclusion or element of notation, which this E-looking symbol means element of, and when you put bars through things or lines through things, that means not. So like when you have an equal sign and you put a bar, like a line through it, it means not equal. Here it's the same story. Okay, so like cat is an element of the cat-dog set, of course. Cat is not an element of, that's what this symbol means, the 0, 1, 2 set. Okay. Now let's get a feel for what the real numbers have. As I said, it has kind of like all the numbers you know. So like 0 is in the real numbers. 1 is in the real numbers. -2, 1/2. Like these like decimals. Like I guess these are called transcendental numbers, apparently. Pi. And like, okay, so yeah, all these numbers are in there. However, the real numbers, the only thing they really don't contain is infinity and negative infinity, which are just symbols for the most part. Okay, so that's all there is. And now let's understand this like subset notation and why is there 3 and not 2? You would think there would be only subset and not a subset. Well, it turns out it's also going to be important to, when something is a subset, to clarify if it's a strict subset or not. And this will also be important in machine learning. How? Well, it's going to be something like, imagine you want to choose the best predictor that's a line. And then someone comes to you and they're like, I want to choose the best predictor that's like this curve or something. And roughly speaking, what's going to happen is they're going to like be searching over some set of curves and you're going to be searching some set of lines. And you might ask like, okay, is this like comparable what they're searching over, like the functions? And what you'll want to say sometimes is like, okay, if the person searching over curves also includes lines, then the search space that they have is like strictly bigger than my space, okay? And so you would say like the lines are a strict subset of all, let's say like function, like polynomials of order 3 or something like that, which would be like curves. So this will be very important to what is going to be called like to distinguish between sizes of like functions you're searching over or predictors. Just a kind of foreshadow. Okay, so this means subset. This means strict subset. So notice the equality symbol here. Just the equality has a bar. Means it's strictly a subset. And this means it is not a subset. Okay, so like there is some element in the set that's not in the other set. So let's look at some examples. Calligraphic X contains numbers 0, 1, and 2. This is a subset of the natural numbers. But more precisely, it's a strict subset, okay? Because the natural numbers has something that's not in X, okay? And it's also correct to write this, because X is a subset of this. Of course, that's true, but more precisely, it is a strict subset. So the like formal definition of this like strict subset thing is that X is a subset, and this set has an element that is not in this set, okay? So you'll see like these things are both correct. Sometimes you want to specify the strict subset part. And so like the natural numbers are a strict subset of the real numbers. For instance, pi is in the reals, it's not in the natural numbers. And there's sets that you can't compare as we saw in this picture. So like X and sigma, or you can compare, but like neither is a subset of the other. So X, the numbers 0, 1, and 2, you know, they're not a subset of the set cat and dog and the other way around. And yeah, the real numbers are indeed bigger than the natural numbers, so they are not a subset. And when you have this like subset, sometimes called subset equal to notation, the set itself is indeed a subset. So like, yeah, like the set, for instance, 0, 1, and 2 is a subset of the set 0, 1, and 2, because it should be read subset or equal to. Okay. Great. Yeah, question. Yeah, so the question is, I've also seen people write strict subset as this instead of this, and sometimes that's fine. Mathematically, people like to do is to make it absolutely clear, because then in some other math places, people end up using this to denote this object as well. So I don't know. It's actually like, as long as the person defines what they mean, it's fine. we're going to define it as this. We're never going to use this. But you should know that it's used sometimes to denote this because it didn't have this line at the bottom. Okay. Now there's, you've probably done calculus and you've heard of intervals. And intervals are just going to be subsets of the real numbers, and particularly like continuous subsets. And the continuous is going to be very vague, but like you probably know what I mean. It's like you look at the number line, you take all the numbers from 0 to 1. That's a continuous subset of the real. And it's going to be important to sometimes, point out if you have if you include the end intervals or not. So these closed brackets mean you include the end intervals, the end and start. If you have these curly brackets, it means it's an open interval, and you can add the closed to the start or to the end, and it just means one side is closed and not the other. Yeah, I guess visually this makes sense. Like open interval, you don't include these points. There's these half open, I think there's sometimes called clopen, which is also kind of funny. And yeah, this like will include the 0 but not include 1. Okay, just be familiar with this notation because it's going to clash with other notation in math that we see in a second, and you're going to have to distinguish between them. Okay, continuing with these sets, maybe the last kind of few operations we need to do with these sets is what are called like, you want to join sets, you want to see if sets have the same things, and you want to like take things out of sets, and that's going to be denoted by like unions, intersections, and set subtraction. And here's the picture again. So you start with like maybe all the natural numbers. And then here, this was like that X set, so it had 0, 1, and 2. Maybe there's another set on the right here that has the numbers 2 and 3. Notice 3 is not in 2. And so you might want to talk about like the set that is, these things joined together. That's going to be the union. You might want to talk about the set that is, look at this set, look at this set, let's look at what's in common, and take the middle of that called the intersection, which is this symbol. And then you might want to take a set like this set, look at the other set, and be like, okay, from this set, I'm going to take out all the elements that are in this set. And the only elements they would have is like 2. So you would take out 2, and you would get this purple set. And that's called set subtraction. So maybe it's like the real symbol. So to take elements out of sets, you don't use the minus sign. Usually you use this like backslash thing. Yeah, okay, maybe I'm not going to, for the sake of time, I'm not going to spend as much time looking like, you can see what it is. In the course notes, it's all defined formally, and probably the best way for you to learn is to read it in your own time, the technical definitions, do some of the assignment stuff, which is going to ask you questions about this, and then you'll be comfortable. Okay, other operation you might want to do is just take what is called a complement, which is like if you have some set and you have some other set that's like called your universe, you just want to take all the elements that are not in your small set. So it's like the complement. It's like the everything else other than what you have. And so like if you have the natural numbers here, this would be an option for this universe. So like you define a universe, it's this calligraphic U, it's like all the numbers or all the objects you're ever going to work with. Let's say they're all the natural numbers. Then if you have some set like this calligraphic X, which was this object, its complement would just be everything other than it. So it would be like all of this, including the 3 over there. And it's, yeah, it has a formal definition, but okay. And it's denoted with a C at the top, complement. Okay, let's get into building sets now. Like I told you how to make sets. You can just take these curly braces and put objects inside of them, whatever you want. It gets kind of tricky when you want to define objects that have certain properties and so on. Like it gets very ugly if they're infinite. And so there's this thing called set builder notation. And it is how you build sets. And we've seen it already. So set builder notation. It's roughly going to be like you write these curly brackets on the sides. And inside, instead of writing all the elements, you say, I'm going to have these elements, and they need to satisfy this property. Okay, so an example of, imagine like for sets we've seen already, this is like overkill, but we can define them in this way, which is the set 0, 1, and 2 can be defined as all of the elements of the natural numbers such that, this is how this bar should be read, they satisfy the property that they're less than or equal to 2. Then you have, let's say, this is, okay, these are a little bit informal, as you can see with the English words. You can define it more formally by like having them satisfy some mathematical property, like this would be something like x, divided by 2 has a remainder of 0. That's what it means to be even. But yeah, in words, it's like all the elements of the natural numbers, but only those that are even. So we saw this set. You can do it for the ones that are prime. That also is a property. You check if there's no divisors or whatever. And then you can define other sets like, all the elements of the natural numbers such that x is in this set and x is not an element of this set, which actually will give you the definition of this like whole set subtraction thing and so on. Okay, so the set builder thing is, let me just maybe remind you why this is important, we'll see it, is that when you get into functions and so on, we already defined like, okay, well, I guess this is the only place we saw, but we defined this set, which is like the set of all functions, such that those functions map x to y, or something like that. And we'll see it in other places later on. Okay, great. We're getting into some useful things now. So there's a set called the power set, to be honest. I don't know if we're ever going to really use it. You can read it in the course notes later if you want. But it's just like the set that contains all possible subsets of a set. Yeah. Okay, so let's get into an important object called the tuple. So notice how these sets didn't have order and they didn't allow duplicates. Well, the tuple is going to allow for both. And we're just, okay. Let me say one thing. There's order, that's something important that you might want to add. There's duplicates, that's something you might want to add. And unsurprisingly, there's, like every variation of those 4 things you could have, and they all have names. So like from what I think, it's like, we've seen sets, they don't have order, they don't have duplicates. If you want duplicates, I think the formal name for it is called a multiset. If you want order, but you don't want duplicates, I think it's called like an ordered set. And if you want both, then you get a tuple, which is a collection of ordered and duplicate things. And we're just going to use this because I'm not going to define all these other cases. So if you want order, or if you want duplicates, just use a tuple. And we wanted that for our data sets, and we wanted that for our features because, like, it mattered that the first index was the number of homes, and the second index was like the distance to downtown, and the third index was the height. If you just use the set and the order didn't matter, it's like, okay, like you don't know what does that first number mean? Does it mean number of rooms, or does it mean, number of floors? I don't know. So these would be important. And okay, so tuples are just like same thing as sets, but they have order, they have duplicates, and they're denoted instead of with these like curly brackets, they now have, right, I guess they're, instead of braces, maybe they're denoted with regular brackets. Okay. And so now, yeah, these are different. This one has an extra 2, so if you have a duplicate, that is a different tuple. Okay. I don't know. There's all sorts of other examples. You get the point, I think. Okay, how are we going to make these ordered sets? We're going to make one way to create these ordered sets, and that's called a Cartesian product, which we'll use very often, as you may have heard earlier. So if you have 2 sets, such as like omega and calligraphic x, you may want to construct ordered pairs, right? Or maybe just sometimes people call them pairs. But you might want to construct ordered pairs of all possible combinations of elements from that first set and the other one. And the way you do that is called a Cartesian product. And it's denoted by this X symbol. And you can do it with more than 2 sets. You can do it with 3 and 4 and so on. For 2 sets, it's just like, look at the first set, look at the second set. For every element in that first set, look at every element in the second set, and pair them up and put them into a tuple. So it's like cat and 0, then cat and 1, then cat and 2. And this Cartesian product will create a new set which contains all of these ordered pairs, all of these tuples. This is the set. Okay, we'll see a bunch of examples in a second. And using our set builder notation, you can see how to like formally define this when the sets get larger and you can't just enumerate everything, which is they look like this. It's going to be the set that contains tuples. So ordered pairs, we give these things a variable name A and B, and it's going to be such that A belongs to the set omega and B belongs to the set Z. and you do every possible combination in this way. Okay, so this, this is actually pretty, this whole example, very important to understand well. And now let's look at objects we've seen before. You might have seen like R2. That'll be like the Cartesian product of R and R. And that'll be like ordered pairs of real numbers. I think I saw a question. Yeah. So the question is, does every like Cartesian product produce maybe tuples of two elements? And the answer is no. We'll see it in a second. Well, why don't I just show you through an example? If you have something like R3, right, which I guess I will write here, and maybe in green I write things that I like kind of annotated in class so people are aware. This is also equal to R, like the Cartesian product 3 times. So you can keep doing the Cartesian product. And when you do it multiple times, it means like, oh, it's going to mean exactly this. It's going to mean now you have tuples of ordered triplets. And, the first one comes from R and so on. So order matters. Like if you put this first, that means it's going to be the first thing in your ordered set and so on. You can see how this is foreshadowing the construction of the data set, right? There you had like a feature and a label, which were ordered pairs. And then you had n objects that you needed to allow duplicates for. So that whole thing is going to be a big tuple that had a power n at the top. So yeah, in general, if you put powers at the top of sets, that just means apply the Cartesian product that number of times. And you can do it with other sets like intervals. So if you do the interval to the power of 2, it's just the Cartesian product of that interval, which you just go back to your set builder notation and remember, it just means this A will always be from this interval, this B will always be from this interval. Okay, now let's define the data set formally. This is what the next 2 examples do. So first, the features. Okay. Let's do the case with the features where X was like 2-dimensional, so you had 2 features. Okay, right now I am of course, very suggestive that X here means features, and like it doesn't need to mean features, but for the purposes of explaining it, we're going to think of it as features. So you have 2 features, something like number of rooms, number of floors, and you have some label which is like the price or something. Well, if I want, feature label pairs, I'm going to take the Cartesian product. And what is it going to look like? It's going to look like the first object is, a feature. The second object is a label, or it belongs to these sets. And this will be like the same thing as R3 to us. And here you can get a little bit confused with a little bit of notation. And this is how we're going to resolve it. So notice that if you just plug in what X is, it's R2, or calligraphic X. And if you just plug in what Y is, it's R. And so here you would get R2 Cartesian product with Y. And if you expanded that, you would get R3, because it's like 3 times R. And so you would have objects of like, for instance, this type, like 2, 2, 200. But, if you expanded it in a slightly different order, which is like you first wrote out what R2 is, which is like an object of this type. And then you took the Cartesian product of this set with this set, the R1, then you would get objects of like this form. And at the end of the day, sometimes people try to make this very explicit, and they'll write things like, okay, green. They'll write things like this, which is like that R, which is R2, like you put brackets that you do this operation first, and then you do it with R, and they'll be like, oh, this is not equal to R, and technically it's true. But there is literally a one-to-one mapping of every single symbol, so most people don't really care. It's called a one-to-one mapping is called a bijection. And so you might also, so you could end up with objects like this. Depending on how you expand brackets, you can end up with objects like this. The only difference is that you have an ordered pair inside another ordered pair. And so it's really not going to matter for us. So either one is going to be correct throughout, okay? Like whatever one you choose. Sometimes this is like, we'll write this to make it clear. This is the features. And then afterwards, this is the label. But yes, at the end of the day, this thing really doesn't matter if it's inside another ordered pair. So that hopefully makes sense. So I'm going to actually just erase this because I don't want you to get confused, because in our class, those are equal, okay? Let me make that absolutely clear. Like this, R3 is equal to R2 is equal to all this, okay? Is even equal to this, whatever you want. Doesn't matter where you put the brackets. But of course, you know, if you have like a tuple that has 4 elements kind of, or like, you know, inside it has a tuple of 3 things and 1, then of course it's not an element of this because these objects were always together of length 3. And here you have like an object of length 3 and then 1. So that's not going to be in the set. So that is definitely not right. Yeah, there was a question about.
So the last one would be of all 4.
Yeah, that's right. So the question is, would the last one be an element of R4? And now, so yes, it's going to be an R4. And just to maybe not confuse you, notice how when you write element of on the right-hand side, the element of symbol is this way. If you write it on the left-hand side, it's written the other way. So that's true. So that was an element of R4, not R3. Okay, now let's get to defining the data set. I wrote this object earlier, and now we can talk about it. So we've already seen what this object is inside. It's a feature label pair. It's a tuple containing features and labels. We have n of them in our data set, so let's, you know, take the Cartesian product n times. If you want to expand it, you can write it out this way, you know. You do it once, you do it twice. This blue just means you've done it n times. Because, yeah, it's a Cartesian product, duplicates are going to be allowed, and so you might, like a specific example is you might get the following data set if you had whatever n is. So you might get like, this is your first feature. Okay, so like with the above notation that we saw before, this object here would be like x1. And we'll talk about this vector notation in a second with that bar. And this would be like y1. And this object, well, this is like x2. And this object, that's like y2. And yeah, and so on. And this object over here is xn, and this is yn. And altogether, this is one data set. It's, you know, n feature label pairs, as you see, and it belongs to this set, right? This is the set that contains all possible n length feature label pairs. Okay, and to not get confused, this set is not equal to the data set. This set contains the data set. And notice there's a slight abuse of notation. Data set. We write it as one word because indeed it is not a set, it is a tuple. Okay, so data set is really this tuple of feature label pair tuples. It has order, it cares about duplicates, and so on. It is not a set that does not care about duplicates. And people will often just write things like this in some papers and so on and textbooks, and it is definitely sloppy. Okay, great. I think I saw something online, so I just want to be clear. And there was like a question, roughly speaking, it's like, is the total set that contains tuples called a set or a tuple? And when you do a Cartesian product, you always get a set back that contains tuples, right? And so this object, this is a good check. This object here, what is it? It's n Cartesian products of this object, inside which are also, so this object is a set. It contains tuples. So it should make complete sense that this data set is a tuple and an element of it. And that the data set is not a set. It's just an element of this object. Okay. Anyways, you'll play around with it, spend some time on your own, get comfortable, and it'll make sense later. Okay, let's get into vectors, which are essentially tuples, except, you know, we're going to want this extra property that usually you get with numbers when you write, like when you write numbers, you usually understand that you can add and subtract and so on with them. When you write tuples in general, you know, unless you define what addition and multiplication stuff mean with them, it doesn't mean anything. And so if you add this extra, what is called structure of like adding tuples and multiplying tuples and some extra things, which I'm not going to define, which are like the properties of what is called a vector space. Well, then you get elements of the vector space are called vectors, and then you can add them and do things. And you can imagine we want to do like, you know, we're going to need to find like the best predictor, and we're going to need to do some sort of like math with these objects. And usually finding the best of something means like optimizing or minimizing. And, when you do this, you're going to need to take like derivatives and so on. And all these things are going to require you to be able to like multiply and add numbers. And so just working with set theory stuff is not going to work for us. So we're going to need to add this extra structure. So this is my long-winded way to say that most of the time when we talk about tuples, especially for the features, we are really going to just call them, like, we're going to assume they're vectors and that we can add and multiply things. Seems like a very, like, something that's usually swept under the rug. It's fine, but you should know. Okay, and yeah, so an example is like when we had these linear, like this line, right? We needed the ability to like take our feature x and multiply it by the number like 200. Or in general, we need to take a dot product. And so we're going to need to do these vector operations. Okay, so yeah, there's a thing called a vector space. That's where the vectors are going to belong to. And yeah, it's going to contain tuples that we can add and multiply by scalars. And okay, there's a property of the vector space. It's something like if you take two vectors, you add them together, you get something in the vector space. You take a vector, you multiply it by a number, you get something in the vector space. That's like the definition of a vector space and it being closed and stuff. That's what I write in this example. We're not going to go over it. And so yeah, that's all you need to know. You can like add and multiply vectors. So let me just be clear. If you had like two vectors like this, like x and y, when you write add, it means, write out the vector if it's 2D. So first you define your vectors, like x will be an R2 and y will be maybe an R2. And you can add them together. And maybe one point to also note, I said this vector space and whatever, and these can be very abstract. For the purposes of this course, the only things we're going to talk about that are vector spaces are the various dimensional real numbers. So like R, R2, R3, and in general RD for our features. And that's all you need to know. That's a vector space, and you can add and multiply things. And so yeah, so an example when you're working with specifically R2, if you take a vector in R2 and take another vector, addition means the following. It's just like add in the corresponding dimensions or the indices together. And if you have a scalar, which in our case is just always going to be a real number, if you multiply a vector by a scalar, then you just multiply every single dimension or index by the corresponding scalar. That's all you need to know. And of course, like this said dog and cat, I haven't told you kind of why, but it's not a vector space. You shouldn't be too surprised. We don't know how to add dog and cat. But you could define it actually. If you define addition properly, you could actually make it a vector space. Okay, but we won't be doing that. And so yeah, vectors are just going to be these elements of vector spaces. And now we get to the transpose notation. Okay, so when we write vectors, like when we write a symbol like this, that's x is a vector, we mean a column vector, so we'll write it like this. And when you put the transpose, it just means write it as a row. So like the transpose of a column vector is the following. And if you do the transpose again, you get back the other thing. It just transforms columns to rows and so on. Yeah. Okay, and we're not gonna, it's technically not an element of R2, but we're not gonna talk too much about that. And at this point, even a little bit earlier, I just want you to not confuse some notation. So let's just take a slight step back. So, okay, we've covered these vector transpose. Next thing is going to be like these dot products and matrices in a second. But before getting there, notice how one of the first objects we saw with like regular brackets and so on was was the intervals. So there's like this interval that uses this notation. And with, you should know from the context, or it'll be told explicitly that something is an interval. And should be clear from context too that something is a tuple. And we'll also make it clear by indicating certain things or so on that that something is a vector. But they kind of, like this, also use the same notation. And sometimes people will use a different notation, like these brackets, to mean vectors. And to be honest, I think I probably should have done that. But now that all the course notes are written with this, I was too lazy to go back and change that. So we're going to have these things. But this is also common. It's just, I don't know. It can get confusing a little bit. Okay, so let's continue with how we can manipulate these vectors. An important operation we're going to do with these is called the dot product, and it is one way to multiply vectors. And a dot product is just denoted by this is how we're going to write it. It's going to be like, you take one vector and you take its transpose, so you write it as like a row, and then you write another one beside it. Sometimes you'll write it like this with a dot. It's the same. Oh, never mind. Forget about the dot thing. They'll just always denote it as transpose times that. But sometimes, okay, sometimes they'll be written just like this. Not in this course, but in other places you'll see this is what the dot product. So yeah, this thing really means take the row, take the column, and you can flip them. It doesn't matter. And so it looks like this. You have X, you have W as a column, and the way the procedure works is you take every single dimension and multiply them together, the corresponding entries, and then add them up. And roughly speaking, you'll hear things like, this tells you like how aligned the two vectors are. Maybe to give you some intuition, like, you know, in 2 dimensions, if you had the following vector, which is like 1, 0, which is like, let's say the vector along the x-axis, and this vector was like 0, 1, which is the vector along the y-axis, well, the dot product for this is 0, right? Why? They're unaligned. So if they're perpendicular, or in general called orthogonal, then they're unaligned. And if they are exactly the same vector, so if this was like 1, 0, then they're perfectly aligned, and you get kind of the largest value of 1. That's another rough way to think about it. Okay. And anyone taking linear algebra will know that there's like lots to say about these vectors, but I'm kind of telling you the bare minimum that you need to know for the course. Okay, and then what you need to know about matrices is that you can think of them as just a bunch of row vectors vertically stacked. And then the only like these matrix operations and so on will just be a bunch of dot products. So like a matrix will just be take a vector, take another vector, transpose it so that it's a row vector, vertically stack it. You now have this like thing that we will use square brackets to denote. And it will look, yeah, it will look like this row vector stacked on top of this row vector. And yeah, so that's one matrix. You can have another matrix that stacks 3 row vectors, for instance. Fine. I don't know what this was. I think this was old stuff. You can forget about that. Okay. And then you can multiply them. And the definition of multiplying them is like, as you've seen with these dot products, which is you're going to take the matrix and you're going to multiply by a vector. What do? You just apply the dot product to every single vector in the matrix, and you're going to get back a vector. So matrix times vector gives you back a vector. And that's all you're going to need to more or less know about linear algebra. And the procedure looks like just, yeah, apply the dot product with this, then apply the dot product with this, and that's what the output looks like. Okay, and there's going to be one more property you're going to need to know about this, which I don't cover now, and like we're not going to, like you're just going to hear about it, which is the inverse of a matrix. And the inverse of a matrix, just like if you take a vector, multiply by the matrix, then multiply by the inverse, you get back the original vector. We'll see it just in a very special case, and that's it. But like that's really all you need to know. Okay, we have like 5 more minutes. I'll get a little started on these functions, and we'll then, yeah, I'll take like 2-3 minutes to give you the high level idea, and then we'll wrap things up in the next class. Okay, so like we've done all this stuff with sets. It allowed us to define the data set. Now we have defined some vectors and so on, and these will be important to define some functions that we're going to use in the future, right? You can imagine that in the future we might want like the function that I said above, which is, you know, this like linear function, which applies the dot products. And so this x will be like the features, and this will be like the slopes that you need to learn from the data set. And okay, and so now let's just really briefly define what function notation looks like. So a function is just going to be some like input-output correspondence. And the way we denote it is like functions will take as inputs objects of some set X, and they will produce as outputs elements of some other set Y. And so you will say like some function is of like this type, which looks like this. It's like It takes objects from X and it maps them to some objects in Y. And yeah, so X is like will be called the domain. Y will be called actually the codomain. Honestly, we probably don't need to distinguish it so precisely, but this is done. And then the set of values your functions actually take might not be all the values in the codomain. Like you might have, for example, this might be like R, and this might be like R, but then your function might be like take in X and just always map it to the number 1. And so the values that the function actually maps to is called the range, and it will always be a subset of the codomain, but it could be a strict subset. And so like visually, it's like the range can be smaller than all these things, but usually, yeah, so sometimes people will write this as the range of the function as well, but we'll use this kind of notation. And so then you can see that for our learner, for our predictors, it was important to define what is the set of objects that come in and what is the set of objects it maps to. And we'll finish that next lecture and get into probability. Okay, well, thank you everyone, and see you Tuesday.